Today we're going to go over topic 1.7, where we're going to be talking about rational functions and their end behavior. So a rational function is just simply the quotient of two polynomials. Okay. So here's some nice examples of what a rational function looks like. It's just a polynomial over a polynomial. We don't have any square roots. We don't have any fraction exponents or anything like that. It's simply just a polynomial over a polynomial. Now, rational functions have end behavior, and what will determine that is the leading terms of the numerator and the denominator. So the thing with the biggest power in the top and the thing with the biggest power on the bottom. And there's three different cases. The first case is if the degrees are the same. So you have a 2 and a 2, a 4 and a 4, whatever. That's going to take over are the leading coefficients. So we say it's going to have a horizontal asymptote at y equals a over b. This is also the ratio of the leading coefficients. The second case is if the degree of the numerator is smaller than the degree of the top. That means the denominator is going to be growing a lot bigger than the numerator, which means the values are going to eventually go to 0. So we say that we have a horizontal asymptote at y equals 0. And the y equals piece is important because a horizontal asymptote is a horizontal line. The last case is that the numerator dominates the denominator, meaning the degree of the numerator is bigger, which means the top is going to grow much faster. So that means it's not going to go to a value, it's not going to go to 0, it's going to go to either infinity or negative infinity. So what we'll investigate in that case is really what's the leading coefficient and what's the difference here. And we'll see examples of all of this, of course. There's a kind of a funny little caveat. In that last case, if the degree is exactly 1 higher in the top than the bottom, then our graph has what we call a slant asymptote or an oblique asymptote. So it's actually going to approach a specific line, still going to infinity and negative infinity, but it's going to approach a line. So we're going to determine if these ones have horizontal asymptotes, or slant asymptote. If they do, we're going to name it. So let's dig into this. So what takes over is the degree. So here the degrees are the same on the top and the bottom. Okay, so what takes over is the leading coefficients, and I like to just circle them there. So this one has a horizontal asymptote. And that's going to be at y equals 3/5. Now I want to show you a graph of what this looks like. So we have a rational function, an end behavior, just like with polynomials. I don't really care about what's happening there's lots of stuff going on here, and we're going to spend lots of time going over that. But what we want to know is what's happening at the ends. And we can see that this graph is approaching a value less than 1, which we now know as 3/5. Okay, in this second one, the degree is bigger on the bottom. So the numerator is less than the denominator, which means we do have a horizontal asymptote. And this one's going to occur at y equals 0. If the degree is bigger on the bottom, that denominator keeps growing more and more, and it will go to 0. And we can confirm that result again by graphing. So this one approaches 0. In this one, the numerator is bigger on the top. So there will not be a horizontal asymptote, but if it's bigger by exactly 1, which in this case it is, then we have a slant asymptote. So here's what this one looks like. So you can kind of imagine a line being drawn right in there. So it's not approaching a horizontal line, it's approaching a slanted line, which is why we call it a slant asymptote. Okay, so I encourage you to try those next. So for these last three, Degree is the same, so we have a horizontal, and it comes from the 4/8, which is 1/2. Bigger on the bottom, so it's going to 0. Degree, this would be degree 0 over degree 1, which means we again have a bigger degree in the bottom. Next, we're going to write limit statements to describe that end behavior. It's still going to come from the asymptotes. Whatever the horizontal asymptote is, that is the end behavior. So here the degrees are the same on the top and the bottom. So I have a horizontal asymptote at y equals 2/6, which would be 1/3. So from both sides, and we saw this graphically, as we go to both positive and negative infinity, my graph is going to go to 1/3. So we say our limit statement, the limit as x goes to negative infinity of f of x is going to be 1/3. And the limit as x goes to, sorry, this should have been negative infinity, goes to positive infinity of f of x is also 1/3. For these, the behavior will be the same if it's approaching a horizontal asymptote. This one, the degree is bigger on the bottom. So we have a horizontal asymptote at y equals 0, which means the limit as x goes to negative infinity of g of x is 0, and the limit as x goes to positive infinity of g of x is also 0. In this last one, the degree is bigger on the top, so there is no horizontal asymptote, but we can still describe the end behavior. So first I'm going to, everything that's not the biggest power, just kind of ignore it. So we're looking at what's left. We've got negative 3x to the 4th over x cubed. Well, if I simplified that, I'd get negative 3x, and the graph is going to behave like negative 3x at the ends. Well, negative 3x, if I were to graph it, is just a line with the slope of negative 3 going through the origin. So as we go to negative infinity, then my graph is going to positive infinity. As we go to positive infinity, then we are going to negative infinity. Okay, next we have a graph provided for us. This one has a horizontal asymptote at y equals 2. So as we go to negative infinity, and we'll just call this f of x, we're going to 2. As we go to positive infinity, we go to 2. Let's see if you can do this one. So for this one, for both going to negative infinity and positive infinity, our graph is approaching a horizontal asymptote of negative 1. So let's take another minute to talk about slant asymptotes. We will be dealing with this more later, but if the degree of the numerator is exactly 1 higher than the degree of the denominator, we have a slant asymptote. Eventually we'll have a way to actually find what that slant asymptote is. But we can look at, for right now, that leading term. Again, and just like we did before, if I take away all the extra stuff, it's just this leading thing that takes over. And this degree is going to be 1 higher than this one. So I'm going to have a over b times x. So that's the slant asymptote, which we'll find later. But right now we can know it's parallel to a over b. So this question says, which of the rational functions has a slant asymptote parallel to the line 1/2 x? So first let's determine if they have a slant asymptote. Here, its degree is the same, so I'm going to have a horizontal asymptote at 1/2, so not. Here, the degree is bigger on the bottom, so we're going to have a horizontal asymptote at 0. Here, the degree is exactly 1 higher on the top than the bottom. Okay, so there is a slant asymptote. And if we take away the extra stuff, I'm just left with an x over 2, which would be 1/2 x. So this one is. Let's check out the last one. Here the degree is bigger on the top, but it's bigger by 2. So it must be bigger than 1. So our answer is 3 only. So that is your introduction to rational exponents, or rational functions and their end behavior.